So it's my great pleasure to introduce Rufus. He will talk about decomposable Seastar algebras and the UCT.
Thanks very much, Julian. And thank you very much to the organizers and everyone for being in the audience, particularly thanks to the enthusiasts who were here last week as well. I'm impressed by the dedication of those people. A lot of this is joint work with Guliang, and it's been an ongoing project with Guliang for quite a number of years now, I guess. This is Guliang, by the way, as probably everyone knows. Is it working? There we go. And some of it is joint work with Arturo Jaime, who's my PhD student. I think he's in the audience somewhere. This is Arturo. So you don't know. So there's several ways to motivate this, and I'll start with motivation. I'll then introduce decompositions and a new invariant of Seastar algebras that we're calling complexity rank at the moment. The main problem is to understand the UCT, which I won't define until about halfway through the talk, what the UCT is, but some statement about K-theory that a Seastar algebra may or may not satisfy due to Rosenberg and Schockert from the early-ish 80s, early to mid-80s, and describe the main results. I'll then say a bit about the proof, and I'll then finish by stating some wildly optimistic conjectures that Guliang and I are willing to make, and I don't know, I'd be just as happy to see them prove wrong as prove right, but either way would be very interesting. About the structure of nuclear Seastar algebras in general, I guess. Okay, so motivation. First of all, a sort of silly convention, so I don't have to repeat the same assumptions over and over again. All Seastar algebras in this talk will be separable and unitable. Neither of those are necessary all the time, but they simplify a lot of the statements. And with the caveat that they are separable and unitable unless they're not. So the bounded operators on L2, when it appears, is not separable, and the suspension of a Seastar algebra is not unitable. So things that obviously don't have those properties don't satisfy the assumptions, but everything else does. If it's called A or B or C, then it is a separable unitable Seastar algebra. Okay. And the theorem, which was proved maybe 5 years ago now, which is due to a large number of people, the finishing steps are Elliott, Gong, Lin, and New, and Quicius, White, and Winter, but building on work of many, many others. And I think it's become traditional in the Seastar classification world to just attribute this theorem to many hands. But it says basically that simple nuclear Seastar algebras, modulo a couple of other assumptions, are classified by K-theory and traces. So the Seastar algebras are themselves isomorphic if and only if the K-theory is isomorphic, including the order structure, and the simplex of tracial states are isomorphic, and that has to be compatible with the K-theory. But basically it says that if you have suitably nice Seastar algebras, then they're classified by K-theory and traces. So this is a very impressive theorem that has been going on since people have been working on variants of it since about the 70s. Now, if you look at the assumptions of this theorem, assuming that the Seastar algebra is simple, or at least something like it, is definitely necessary in this level of generality. This is going to be hopelessly false without that, and it's a fairly natural assumption anyway. This assumption here, nuclear dimension at most 1, I'll say what that means in a minute. That is also very necessary. It's a fact that if you have a simple nuclear Seastar algebra, then it will have the same K-theory and traces as a different one, which also has nuclear dimension at most 1. So you have to make that assumption. The theorem can't be true without that assumption. The remaining assumption is something K-theoretic, which is satisfying the UCT. And this I've put in red, it's different. And this might not be necessary. So the last kind of question necessary to get sort of the strongest possible classification theorem in this context, strongest reasonable classification theorem, is to get rid of this satisfies the UCT assumption. All right. And that's what will motivate the talk. Before doing that, though, I'll state the definition of nuclear dimension at most one. Oh, yeah, Willie? Question?
If you, I mean, instead of say satisfy the UCT and classify by K-theory and traces, you say that they are isomorphic in KK. Does this?
Right. Well, being isomorphic in KK doesn't say anything about what happens to the traces necessarily. And yeah, for some classes of Seastar algebras, you can get rid of the UCT assumption if you're willing to make a KK theoretic assumption. So for Kirchberg algebras, for example, if you're willing to say isomorphic in KK, and there's no tracial data anyway, purely infinite case, then it's fine. In general, the UCT comes into this proof in several different ways, though. One of the ways it comes in, which is the Tecretius-White-Winter contribution, is that you need the UCT to prove that a C-star algebra, I'll get the assumptions right, a stably finite C-star algebra with an amenable, faithful amenable trace is quasi-diagonal. That's an important ingredient in this theorem. And that needs the UCT itself, even though it has nothing to do with K-theory in its statement. There is some structural ingredient that you need, which also requires the UCT. So it's used in several places, not merely to pass from KK theory to K-theory. Sorry, vice versa, I should have said that the other way around. Does that answer the question?
Yeah, thank you.
Okay, so nuclear dimension at most one, what does that mean? Means this. So look at the class of C-star algebras of this very nice form. So C0y tensor F, and I'm already breaking my rule that everything is unital. This is one that's obviously not unital, need not be unital. With Y a closed subset of this half-open interval and F finite dimensional, so it's a very easy class of C-star algebras. Basically cones over finite dimensional things, more or less. And then nuclear dimension at most more means the following. This is not the definition, it's a theorem that it's equivalent to this. But it says that locally, so if you're given any finite subset of your algebra and any epsilon, then there is a positive contraction, so a positive element of norm at most 1, and C-star subalgebras C and D, which are in this class C, so they have this very nice form. So that first H is approximately central. Simple C-star algebras can't have non-trivial central elements, but they have lots and lots of approximately central elements in general. So fact. So it's approximately central, and it approximately multiplies X into C, and 1 minus H approximately multiplies elements of X into D. So this belongs epsilon means is within epsilon of an element of that set. Okay, so it's at most epsilon away from an element of that set. Okay, so it sort of says that you can use this element H to cut the C-star algebra into 2 bits, and each bit is of this very nice form here. Okay. This looks kind of a strong assumption. It is kind of a strong assumption, but it's also all your favorite examples of simple nuclear C-star algebras, unless you have very exotic taste, do satisfy this assumption. So all Kirchberg algebras, all purely infinite C-star algebras, simple nuclear C-star algebras satisfy this assumption. Irrational rotation algebras, Yes, yeah, and anything at all that most people are interested in most of the time satisfies this assumption. It's very, very general. Okay, so motivating question, which is what I mentioned already. Is this UCT assumption actually necessary? So is the UCT, whatever it is, I'll state it later, state a version of it later, is it automatic for C-star algebras of nuclear dimension at most 1? Okay. Now, the nuclear dimension at most 1 thing is a red herring, because if you combine results of Kirchberg and all these people, Brown, Bosa, Sarto, Capricious, White, Winter, asking that C-star algebras of nuclear dimension at most 1 satisfy the UCT is exactly the same as asking if all nuclear C-star algebras satisfy the UCT. So that's an old question going back to the paper of Rosenberg and Schoppett, the original paper from the mid-80s. So it's the same as that question, which is a well-known open question for 30-odd years now, I guess. So that's really the big question. Do all nuclear C-star algebras satisfy the UCT? That's what we would like to know. So going backwards, my second goal in this talk is to introduce a new sufficient and also sometimes necessary condition for the UCT in terms of decompositions very much in this style here. Cut the C-star algebra into 2 simple bits. And my first goal in the talk, though, is to discuss what those decompositions are and associated notion of complexity for C-star algebras based on those decompositions. So I'll start with that. We'll start with the C-star algebraic stuff, the purely algebra stuff, and then I'll start talking about the KK theory and K theory later in the talk. Okay, so that's where we will go, and I'll now introduce one of the main definitions. All right, so this is modeled on the definition of nuclear dimension at most 1, but it's a bit stronger. So you start with your favorite class of C-star algebras. One of my favorite classes is the finite dimensional C-star algebras, and that's already quite interesting. This definition has non-trivial examples and content in that situation. So your C-star algebra decomposes over that class, say, of finite dimensional things. If again, it's a local property, so you take any finite subset of the C-star algebra, any epsilon, and again, there's a positive contraction, and the C-star subalgebras C, D, and E. So in general, this isn't quite correct, but if they're finite dimensional, it is. You can just pretend that E is the intersection of the other two, and you should think of it that way. And you get similar conditions to nuclear dimension 1. So the H is almost central with respect to the given local data. It almost multiplies things into C. It also, 1 minus it always multiplies things into D. And if you multiply H by 1 minus H, then that multiplies things into this subalgebra E, which you think of as the intersection. E is almost contained in both. Again, if you're only working relative to the class of finite dimensional things, you can assume it's the intersection, because drop that condition. I don't know if you can drop it in general. I think you probably can, but that's quite hard to prove. Will be quite hard to prove. And H almost multiplies E into itself. And again, that condition, if you're happier, just replace it by multiplies E into itself. It's equivalent, it doesn't make any difference. When I say, by the way, E is approximately contained in C, these are vector spaces, so what does that mean? It means that any element of the unit ball of E is within epsilon of an element of C. That's what this expression here means. For example, you have to restrict the unit ball, otherwise you can scale and it's nonsense. Okay. All right. So it's like the definition of nuclear dimension 1, except with additional data on the intersections, okay? On the intersections of the 2 nicer subalgebras that you have. So morally, this is a nuclear dimension less than or equal to 1. But you don't just have the two subalgebras, you have additional data on their intersections, and that makes all the difference. Makes the property much stronger. Okay, so schematically, you have a picture like this. And this picture is sort of honest when all the Seastar algebras involved are finite dimensional. You have your element H and your element 1 minus H. Those are like a partition of unity in the commutative case, or a partition of unity, of course. And then you've got the bits of H which lives inside E, which we can call H sub E. You have a projection P, which you can think of as being the spectral projection of H, nope, at 1. Projection Q, which you should think of as being the spectral projection of H at 0. This thing H sub E, I shouldn't write it like that, but you can think of the identity of E as being the spectral projection of H associated to the open interval between 0 and 1. So you split up the identity in that way. All the action is happening inside E in some sense. And then your Seastar algebra is at least locally covered by C and D, and their intersection is, okay, living there somewhere. It's a very rough schematic of what's going on in this situation. Right. So that's a key definition for the talk. It's a little bit technical, but think of it as nuclear dimension 1 plus a little bit more, if you like. But again, locally, you can cut the Seastar algebra into 2 bits, which are very nice, maybe finite dimensional. Nice too. Okay, so I'll do some examples and then pause for a moment. So examples that decompose over the class of finite dimensional Seastar algebras, these are mainly essentially due to other people. They thought they were proving something else, but they were really proving this, which is a stronger statement than what they were proving. So old theorem of Ian Putnam from the late 80s, that if you take a Cantor minimal system, the integers acting on the Cantor set, then the cross product has this property. It decomposes over the class of finite dimensional Seastar algebras in this sense. Theorem of Winter and Zacharias, they thought they were proving that the Kunz algebras have nuclear dimension 1, but they were actually proving this much stronger statement, that they decompose over the class of finite dimensional Seastar algebras. It's essentially due to them both. Also essentially due to Winter and Zacharias, again, they thought they were proving something weaker, but they weren't. They were proving this, which is that the uniform row algebra of the integers, so that's the cross product of the bounded functions on the integers by the canonical translation action, that decomposes over finite dimensional things in this sense. AF algebras, I should maybe mention, so things that are locally finite dimensional trivially have this property. Open question, our probably favorite example in non-commutative geometry. Does the irrational rotation algebra have this property? I don't know, much to my annoyance. I tried quite hard to prove this, and I couldn't, sorry. But I'm sure the answer's got to be yes. But if someone else can prove that, I'd be really happy. So sorry about that. Don't know. But I'm sure the answer is yes. Okay. So those are basic examples satisfying this definition. So as you can see, it's a pretty broad class. One thing to note is that these things are very finite, like the type 2 case in the von Neumann algebra situation, so these are stably finite. These things are very not like that. They're like the type 3 case in the von Neumann algebra situation. They're purely infinite. So very different classes of examples. This is not like being locally finite dimensional. It really includes large classes of Seastar algebras with very different behavior. Okay. So any questions about the definitions or examples so far?
But Rufus, I see that is decomposable over something a little bit more flexible. Right? I mean, if you allow the entries of the matrices to be like C0 of like a space. So
I don't know. Sure, it's true, but I don't know. Do you know?
I mean, This definition you give, I actually, decomposable. I mean, if we replace the finite dimensional Seastar algebra by something, let's say, just say type 1 Seastar algebra.
Yeah, okay. So if you replace C by the class of type 1 Seastar algebras, does A theta have that property? I actually know the answer to that, Guliang. I'm sure it's true.
No, unless I'm confused. So the usual like dynamic asymptotic dimension 1, right? So if you decompose the circle in...
I see what you mean. Yes, of course, you're right. Yes, you're right. If you allow type 1 things and don't assume, yeah, that's fine. Yes, that's true. Yes, it certainly decomposes over the class of type 1 things in this sense. Yeah, that's fine. Yes, sorry, my bad. Yeah, you're completely right. And even over the class of things that look like this, that's true as well. Yeah. Sorry, Julian.
Yeah, that's okay.
Do you know anything about how this property behaves under inductive limits? That would probably be key to answering the question about A theta.
Yeah, it behaves well under inductive limits. As long as the class you're decomposing over, I'll say a bit more about that in a minute, as long as the class it decomposes over behaves well under inductive limits. But yeah, for example, decomposing over finite dimensional things is preserved under inductive limits. So I would conjecture as well as this that any AT algebra of real rank 0 decomposes over the class of simple, maybe throw it simple, decomposes over the class of finite dimensional Seastar algebras, but I can't prove that either. So, but that's probably just because I'm incompetent and don't understand simple Seastar algebras very well. So I'm sure if I got a proper expert, they could do it. So yeah, it does behave reasonably well. It has fairly good permanence properties. Inductive limits are certainly fine. Any other questions or? All right. So very quickly, you can also talk about weak decompositions, which basically means you forget about the E. So same definition, just forget about the E, the intersection. And then I couldn't quite prove the thing I would like to prove. This is all with Arturo, this is both of us. But we can at least get something like the following. If the Seastar algebra is simple with at most finitely many tracial states, then weakly decomposing over the finite dimensional things is the same as having nuclear dimension 1 of real rank 0. So it ties into these very well studied Seastar algebra properties. Real rank 0 means that any self-adjoint element can be approximated arbitrarily well by an invertible self-adjoint element. So if you drop the condition on the intersection, this relates to very well-studied properties of Seastar algebras in a very nice way. This condition is annoying, and I would guess most of it can be dropped, but that's the best we could do. Again, let's try and get some more experts involved and prove some of this for us. Okay, so the second kind of invariant, which seems interesting from the point of view of pure Seastar algebra theory, is that you can define a notion of rank for a Seastar algebra. So for an ordinal number alpha, could be finite, but doesn't have to be. If alpha is 0, d alpha is the class of AF Seastar algebras. And for other alpha, it's the class of Seastar algebras that decompose over the smaller class of things. So, okay, this gives a kind of ordinal number valued notion of complexity for Seastar algebras. Motivating examples, if you have, say, a discrete group, then there's a notion of decomposition complexity for discrete groups that covers many examples. Live in one of these classes which have finite complexity in this sense. So that includes amenable, elementary amenable groups, linear groups, hyperbolic groups, huge class of examples. And in that case, the complexity rank of, again, this cross product is bounded above by that geometric notion of complexity in that setting. Okay. And the definition is defined to make this, is set up to make this work. This is not that easy to prove, but it shouldn't be super surprising either. So that gives an interesting notion of rank, and on my next slide I'll just point out that it really is interesting. So one of the things about nuclear dimension when it was first defined is people assumed it would be an interesting invariant of simple C-star algebras, and it is in the sense that whether or not the C-star algebra has it is interesting. But it turns out that the only possible values of nuclear dimension in the simple case are 0, 1, and infinity. Okay. All right, that's a hard theorem that's been proved pretty recently by, again, lots of people involved. This doesn't do that. This is more interesting. So I've mentioned Kirchberg algebras already a few times, but here's the actual definition. C-star algebra is a Kirchberg algebra if it's nuclear. So the analog of injective in the C-star algebra sense. And if for any non-zero element there are other elements, so that if you multiply that thing by it, you can move it to get the identity. So it's simple and infinite in a very strong sense. Okay? That's what Kirchberg algebras are. This certainly implies simplicity, but it's much, much stronger, of course. And okay, if you throw in the UCT, that's really important. Then the complexity rank of the Kirchberg algebra is 1 if and only if it has torsion-free K1 group, and otherwise it's 2. Okay. Always. So it always takes one of those finite values, and you can classify exactly when it has the value 1 and when it has the value 2. So, okay, it's at least takes those two values. Getting lower bounds is probably very difficult in general, but you can at least do this, that having torsion in K1 is an obstruction to being in the rank 1 case. Having complexity rank 1, by the way, means you decompose over the class of AF algebras, but that's the same as decomposing over the finite dimensional algebras. That's the class I was talking about earlier. Very nice class. Okay. And again, that should be contrasted with this theorem, which says that by all these people, Johan Bose, Brown, Jessica Soto, Aaron Taquisha, Stuart White, and Bill Winter, that if you have any Kirchberg algebra at all, then it has nuclear dimension 1. Okay, so that's the only value the nuclear dimension can take on that class. And they don't need the UCT to prove that. We do, they don't. So this really uses the Kirchberg-Phillips classification theorem for Kirchberg algebras in a strong way, multiple times over and over again. And that's why we need the UCT. And it would be really nice to prove it without the UCT. I'll mention this again near the end of the talk. If you can prove this, or even something much, much weaker, without the UCT, that's actually enough to get the UCT to be always true for the C-star algebras. So it implies the UCT for all, whoops, that too, but for all nuclear C-star algebras. Right. So combined with this theorem, that's kind of suggestive. Nuclear dimension 1 looks like it's not that much stronger than this complexity rank 1 notion. Sorry, weaker, but it probably is quite a bit weaker. So it'd be extremely interesting to establish something like this theorem, and you don't need all of this. You need something much weaker. And that would give you the UCT in the maximum, well, not the maximum, but the degree of generality you wanted for all nuclear C-star algebras. Okay. So yeah, that's would be very interesting. Right, so that's all I want to say about the decompositions in general. I'll move on to the K-theory stuff now. Any other questions there before we do that? This comment here follows from the main theorem, by the way. That's the result of Kirchberg. Okay, so let's assume this is really not necessary. but assume for simplicity that A is nuclear because it lets me state something in a simpler way, and separable and unital as usual. And let B be any C-star algebra. Let HB be the standard Hilbert module, so it's little L2 of the natural numbers tensor B. And take any faithful infinite multiplicity, so that just means you take a faithful representation, add it to itself infinite many times, and unital representation of A on B of L2, and then identify that with a subalgebra of the adjointable operators on this thing in the usual way. So whatever, it's just a nice representation of A, kind of in general position in some sense on this Hilbert module. And then you can define the localization algebra of A and B to be the C-star algebra of continuous bounded functions from the half line to the compact operators in the sense of Hilbert module theory on this C-star algebra. So that's just the compact operators on L2 tensor B. With the additional property that any element, any one of these continuous functions asymptotically commutes with any element of the C-star algebra. So it's a set of paths that asymptotically commute with the original C-star algebra. This doesn't need nuclearity or unitality. If you state it correctly, I was just a bit lazy to state the full version. But for K-theory, this is KK theory. Okay? So if you don't know the definition of KK theory, just take this as the definition. It's not a very nice thing to do, but it works. So the KK theory of these two C-star algebras is exactly the K0 group of this C-star algebra. It's the K theory of this collection of things that asymptotically, these things that are basically in the stabilization of B, but asymptotically commute with A. That's KK theory. Okay. That's the theorem of Mario Startlat, myself, and Jin-Chao Wu, modulo a minor technicality that Guliang and I fiddled with later. Basically, that's correct. Okay. So that's KK theory, and here's an ad hoc, and sorry, with apologies to Jonathan, but this is an equivalent formulation of the UCT, which appears in the original paper of Rosenberg and Schockert, that a C-star algebra satisfies the UCT. So you can take this as a definition if you don't know what the UCT is. Basically, if K-theory determines KK theory, so if having 0 K-theory implies that you have 0, so for any other C-star algebra B, if that C-star algebra having 0 K-theory in both dimensions implies that the corresponding KK groups are 0. That's an equivalent formulation of UCT. So K-theory determines KK theory. And that equivalence is due to Rosenberg and Schockert. It appears in their original paper that this is equivalent to the version that we all, most of us probably know better. So important open question, which I've mentioned several times already, certainly well motivated by the Elliott classification program, but it's also would be very nice to know this in general. Do all nuclear C-star algebras satisfy the UCT? And then the big theorem, the main theorem that Guliang and I proved, the difficult theorem, the most difficult theorem for ones I'm going to mention today. The class of nuclear C-star algebras that satisfy the UCT. So, e.g. So this is large. Everything I've mentioned so far is a nuclear and satisfies the UCT. But you can include things, for example, type 1 C-star algebras. They're all nuclear. That's pretty easy depending how you define these things. And they all satisfy the UCT. That's in the paper of Rosenberg and Schockert. The class of type 1 C-star algebras is definitely not closed under decomposability, but you could look at the things which decompose over that class. That's a very large class. Some could well be all nuclear C-star algebras. And then that will satisfy the UCT. So it gives you a direct proof of the UCT based on the local structure in that situation. In particular, if you've got complexity rank alpha in the sense I mentioned before, then you satisfy the UCT. That's the stuff which is built from finite dimensional things by taking successive decompositions. Okay. And that includes, like I was saying before, many of our favorite examples of nice C-star algebras. Okay. All right. So that's the main theorem, and I'll spend a bit of time now talking about how to prove that, which is somewhat involved. But any questions about the theorem, though, before I start doing that? All right. So, okay, this is getting a little bit technical now, but I want to state some of the ideas that go into the proof, or at least give a sense of some of the ideas that go into the proof. So hopefully they'll be useful elsewhere anyway. So step one, using the localization algebra I mentioned before, you can establish a Milnor exact sequence, which looks like this. So this is an analog of Milnor exact sequences that were established by Claude Choquette starting in the 80s, but then also through the 90s he continued to work on this sort of thing. Proved some really beautiful results along these lines. So morally what's going on here is you fix a finite subset of the C-star algebra A, so that's this X here, and parameter epsilon. And then this group KK, it is a group, KK epsilon XB is part of the K theory, I should say, of B, that commutes with the set X in the sense earlier, so you fix a representation of A up to the parameter epsilon. Okay, so being more precise about this, okay, this is a little annoying to state directly, but it's not too bad. It's basically just K theory. It's just a way of defining K theory. So you fix a nice representation of A as before. You look at the projection onto the even path of that graded representation. And then you look at projections which almost commute with X and which agree with this nice canonical thing up to a compact operator, or in the, sorry, the stabilized C-star algebra B. Then you take the path components of that set, and that's your controlled KK theory group, as we call it. So part of the K theory of B that commutes with X up to epsilon. Note that the KK theory of epsilon empty set B is just the K0 group of B. Okay. So it's just a way of defining the K0 group, and you think of it as the bits of the K0 group that almost commute with X. Okay. Of course, you have to also take the homotopies to almost commute with X as well, so you have to change both the elements and the equivalence relation. Okay. So that's what that thing is. It's a nice abelian group, which you can prove. These are abelian groups. They obviously fit into an inverse system because if y is bigger than x and delta is less than epsilon, then it's easier to commute with x up to epsilon than it is to commute with y up to delta. So you can just forget that you have the stronger commutativity property. And that gives you obvious canonical forget control maps in that situation. Okay, so you have an inverse system. And then you have this thing here, which is the inverse limit of all those over that inverse system. And then you have the first derived functor of the inverse limit, which goes there, but with the suspension appearing instead. And that goes there on the left. All right, so that's how that works. The maps are the obvious ones. These are paths that asymptotically commute with A. So to get a map to this, you just look at that path and you evaluate it at larger and larger points, so it commutes with larger and larger subsets and so on and so forth. This map is a bit fiddlier to do, but it's, again, not that hard to make these maps. I should also comment that these things are things that people know and like already in the fine structure of KK theory. This is Rodin's KL group. whatever that is. And KK theory carries a canonical, possibly non-Hausdorff topology. That one is for closure of 0 for that topology. If you don't know what that topology is, it doesn't matter because it's for canonical topology arising from this inverse limit. You take the inverse limit topology on this abelian group and you pull it back to a KK theory. That's for canonical topology on KK theory. It's all very compatible with this system in a nice way. Right. So first of all, you get that Milnor exact sequence, which was established by Guiliang and I, and the first paper we wrote on this. There's 2 long papers where this all comes up. So it's very nice structurally. It gives you a fairly concrete description of KK theory. It's hopeless for things like the functoriality properties of KK theory, but to get a concrete grip on what KK theory is, it really helps. Okay. So that's step 1. Prove that Milnor exact sequence. And then you can characterize the UCT in the following way. Okay. So you prove following are equivalent. This is still step 1. Maybe this should have been step 2. So general Seastar algebra. It doesn't need to be nuclear for this, by the way, or anything else really. This is true in general. But satisfying the UCT is equivalent to the following statement. For any other Seastar algebra B with 0 K theory, and any finite subset of A and epsilon, remember if B has 0 K theory, the UCT means that the KK theory vanishes. Okay, so thinking about that inverse system before, that should tell you that the connecting maps in the inverse system are 0 if you go far enough up the inverse system, and that is indeed true, but also the converse is true as well. If the connecting maps far enough the inverse system are true, then the KK group is going to vanish. Okay, so satisfying the UCT means that in the inverse system associated to B, you have to take a suspension for some stupid technical reason, but the maps in the inverse system eventually have to be 0. The inverse system is kind of trivial. It satisfies a trivial Mittag-Leffler type condition. Okay? So that's very nice. And that gives you a concrete grip on the UCT. Second super important ingredient, which is some very technical fact from general Seastar algebra theory and von Neumann algebra theory, really. So back in the 70s, Alan Kohn proved that amenability, some property of the Nark algebras, which I won't define, implies nuclearity if you're dealing with a Seastar algebra. About, I don't know, 5-ish years later, Uffe Hagerup established the converse. The nuclear Seastar algebra is always amenable in the sense of Barry Johnson. And what that lets you do is something that's really crucial from a technical point of view, and kind of amazing to me that this is true. But it says that in this theorem, if the Seastar algebra A is nuclear, which is the only situation we care about, you can do some clever averaging arguments, which is due to these people. They were working on something completely different. They were proving that, oh, we can go into it. They were proving something else. It's nothing to do with KK theory. You can prove that there's sort of a uniform bound on how much further up the inverse system you have to go in order for the maps to be 0. And yeah, that's very necessary to prove anything. It's kind of amazing that this is true, but it is. You need nuclearity for that. I would speculate it's false without nuclearity, but I'm not sure. Okay, so that's really, that's a technical ingredient, but really important is this very difficult theorem of Hagerup that nuclearity implies amenability. Yeah. That's one of the places, by the way, that nuclearity is used in this theorem. The other one is Kasparov's version of Wojciechowski's theorem of Hilbert modulus. It's used in those 2 ways. Okay, so step 3, which is the most technical, at least of the bits we did, is that you have some sort of approximate Meyer-the-Torus sequence in this setting. So very, very roughly, you can prove something that looks like this. So you want to prove that some forget control map like this is 0. Now, given the x, you can find an h, a c, and a d, and then you can find a y, which also almost commutes with h, and you can find splitting maps like this. So this is almost in C, that's in D, and that's in E, and you can use the UCT for C, D, and E to kill all those groups on the right and left. And this map has a kind of exactness property. It's like splitting the Seastar algebra into 2 ideals locally. And it has the exactness property, but when you do this splitting, if whatever you started with goes to 0 over here, it does, because you can choose these, you can kill these groups using your assumption of the UCT. Then the image of it, once you forgot control, is in the image of some boundary type map coming from this group. Okay? But you can make that 0 as well, using the fact that E satisfies the UCT, and that does it. That kills the image under the forget control map, and that finishes the proof of the theorem. Okay, so it's yeah, getting the details of that right is fiddly, but that's the basic idea. On some level, this is all elementary K-theory, but it's quite technical to get everything completely correct. Okay, but that's the basic idea of the proof of the main theorem, and it's done at that point. I've got 3 minutes, so I'll state my or mine and Guliang's insane conjectures. Okay, which Guliang, feel free to, you know, disown these if you like, but we put them in the paper, so we should stick with them, I guess. Yeah. All nuclear separable unital Seastar algebras. Okay, throw in an assumption, which means there's a lot of projections. Then you can decompose them, decompose them, decompose them over and over again until you get down to finite dimensional things. That's conjecture 1. Similarly, throw away the assumption that you have enough projections, and you can do the same thing, except eventually you get down to type 1 things. Okay, so you can take any nuclear Seastar algebra, decompose, 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 maybe transfinitely many times, and you can get down to the type 1 Seastar algebras. Okay. Thanks to the main theorem, either of those applies to UCT for all nuclear Seastar algebras. But so do many other much weaker things. So thanks to a theorem of Kirchberg, it would also be enough to prove this. Any nuclear Seastar algebra satisfies the UCT if and only if any Kirchberg algebra with 0 K-theory has complexity rank 1. Okay. Or in other words, i.e. decomposes over the class of finite dimensional Seastar algebras. So it has this very nice structure where you can locally cut it into 2 finite dimensional bits, and the intersection is reasonably well behaved. So there's a partition of unity which cuts it into 2 finite dimensional bits, but also so that the intersection is well behaved with respect to that partition of unity as well. Okay, so I assumed it was a 50-minute talk, so I'm out of time now, and that's my last slide anyway, and I will stop there. So thanks for your attention.
Well, thank you very much, Rufus. Are there any questions or comments?
Just a little thing. This epsilon over 8, wasn't it also in some previous paper of yours on this controlled K-theory?
It's kind of the same epsilon over 8, yeah. It's a lot harder to prove this fact. It's to do with the following fact: that if you have an element in a Seastar algebra, self-adjoint element in a Seastar algebra that satisfies x squared minus x is less than epsilon, then x is within about epsilon over 8 of a projection-ish. So it's to do with the fact that things that are almost projections in a Seastar algebra are close to things that are honestly projections. Yeah. So the results of these people let you approximate your original projection by something that commutes much, much better, but is only approximately a projection, and then you have to replace that thing by an actual projection. That's sort of what's going on. Yeah. So, yeah, I'm impressed you spotted that.
Well, I mean, the 8 is not, you know.
Yeah. Yeah, I mean, yeah, this theorem, or this fact here, by the way, with the gamma and the delta and the epsilon, there are explicit estimates for the delta and the gamma, but they're something like epsilon over to the 100 to the power of 100 to the power of 100. They're stupid numbers. So, yeah, they're not over 8 anymore.
And that's this Milnor type of sequence. Does it let you interpret, I mean, KK of AB in terms of the pro system? I mean, like,
yeah,
depends on the system, but on the suspension. This is what confuses me. So like the B without the suspension is not there in the conditions, right?
no, sorry, the suspension is there in Schochert's classical version of this.
No. But when you write the condition later on, I mean, the thing that you conclude for the UCT,
yeah, I mean, the issue is that the K theory of B is 0 if and only if the K theory of its suspension is 0. So
yeah, sure.
Sure.
Yeah, no, but okay, but yeah.
That's by the way why you have to assume here K theory of 0 is K theory of B is 0 in both degrees. Being 0 in degree 0 is relevant here, and being 0 in degree 1 is relevant here. You need both.
Yeah, but so you cannot, I mean, you could consider like, I don't know, the pro system of the KK epsilons,
right.
And whether that or the addition of that, and the same thing with the suspension, will recover all the information of K theory, of K theory.
Yeah, I mean, that presumably, I mean, in some sense, this tells you that that's true. I haven't. We probably should have tried to write it in terms of categories of pro systems or something, and there might be a cleaner approach to it. Some people, I think Lars Hesselholt, you know well, told me I should do something like this years ago, and I never did. But probably we should. Probably it's the right thing to do. Yeah, I didn't think about that, but maybe there's a clean way to set up KK theory in this sort of language, and that might be nice for other purposes. Yeah. I would hope so. I would hope this stuff has other applications.
Okay, thanks.
Yeah. I suppose here one of the flexibility is that X has no algebraic structure, has no.
Yeah, I mean, one thing you can do with this, for example, is X, as Guillaume says, X has no algebraic structure. So in principle, you can use this to define KK theory where the object in the first variable is an operator system or something nice like that. Same idea will work.
Yeah,
maybe.
I think Alan asked that question when I gave a talk.
But I think Walter is working with some student on this problem. So I mean,
okay.
Exactly. I mean, and I think it's a very, very good problem actually, because it would give more flexibility indeed. I mean, yeah.
Yeah. Any other question or comment?
I have a couple of things in the chat. Okay. Oh, that's not a question related to a talk. The person who asked the question in the chat, I will write in can you send me an email later to remind me, and I will get back to you.
Okay.
Thanks.
Okay.
Thanks, Rufus.
Yeah.
Thanks.
Thanks, Rufus. Yeah. Thanks a lot.
Yeah, thank you.
Yeah.
Yeah.